great talk learners. Welcome to today's technical sciences lesson. My name is Musa Zulu, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, again, great talk learners. Today, our area of focus, knowledge area, we're going to be doing chemical change. And the specific topic that we're going to be looking at the grade 12 is electrochemical cells. One of my favorites there, I have to say. I like anything that has electricity in it. Electricity is a very, very interesting concept to me. So it's one of those topics that I really enjoy when I learn more about it. And I do tend to learn more about it almost every time I encounter it. So our topic for today is electrochemical cells. And that's what we're going to be dealing with. Specifically, what we're going to be looking at in electrochemical cells, grade 12, is just trying to revise the issue of a galvanic cell. We're going to be trying to revise the issue of a galvanic cell. That's what we are going to be focusing on mostly when it comes to the electrochemical cells. You'll remember that you've touched on some of these things last year when you were introduced to redox reactions, oxidations, reductions, and all of those things. So that's what we're going to be using and applying in a galvanic cell for today. Right. Our objectives for the lesson is that by the end of the lesson, we expect that people are able to define a galvanic or voltaic cell. Very, very important. Grade 12, this cell can be called galvanic. It can also be called voltaic. So it's important that I bring this term to your attention, because sometimes the examiner will, instead of using the word galvanic, they will use the word voltaic. So you must be familiar with the two terms. It's either galvanic or voltaic cell. So you must not panic or be surprised when you see the term voltaic. It's still the same or as galvanic. Must be able to define an electrolyte. It's very important to define this and also to understand an electrolyte and how it works, especially at basic level, because that's where we'll be applying it. You must be able to predict half cell in which the oxidation or reduction takes place. So you must be able to predict that in this half cell, there will be oxidation taking place. In this half cell, there will be reduction taking place. And then from there, after being able to predict whether the oxidation, you must be able to then write down the half reactions that occur at the electrodes. Be that half reaction is the oxidation, you must be able to write the oxidation half reaction, or that half reaction is a reduction. You must be able to write down the reduction half reaction. And then after you have written down the reduction half reaction and the oxidation half reaction, then you should be able to write the overall cell reaction. It's called the overall cell reaction or the net. Sometimes they refer to it as the net ionic reaction. It's the net ionic reaction. So it's very, very important that you are able to write this overall or net ionic reaction. And then from there, you must use a cell notation. So you must be able to write a cell notation or use a cell notation or cell diagram to represent a galvanic cell. So a galvanic cell is represented using sometimes a cell notation or a cell diagram. And then lastly, you must be able to use the table of standard reduction potential to calculate the EMF of a standard galvanic cell. So, but this table of standard reduction potential, grade 12, we'll also be using it for the prediction of where oxidation takes place, where reduction takes place. We'll also be using it for the writing of our half reactions. Then we also use it for the calculation. So this table becomes extremely, extremely important, the table of standard reduction potentials. Okay, what is it that we expect that you must come into this lesson knowing already? The expectation is that at least by now, from the previous grade 11, you are able to differentiate between oxidation and reduction. As I've said before, you've encountered redox reactions, and the word redox reactions, the word redox is a combination of two words, where red is a part of saying reduction and ox is a part of saying oxidation. So redox reaction is reduction, oxidation reactions. So it was halved and then combined into a word that says redox. So people, I am sure that you have encountered this before in the previous grade in your grade 11. So we expect that you must be able to differentiate between the two to say, what do we mean when we say a reduction half reaction? What do we mean when we say oxidation half reaction? then you must be able to differentiate between oxidizing agent and reducing agent. I find that a lot of learners will understand oxidation, they will understand reduction. However, they will then struggle with the agents to say an oxidizing agent or a reducing agent. So we will try and speak about it so that a person, by the end of the lesson, they understand it. But we expect that at least we have some knowledge of it by now. Then you must be able to define an electrode or know at least of an electrode. That's what we expect by now, that you must be able to do that. Then lastly, we expect that you should be able to distinguish between an anode and a cathode. So all of these things, when you can see, they are related: oxidation, reduction, anode, cathode, electrode, oxidizing agent, reducing agent. These things they are related. So when you know one, you should be able to know the others. Okay, but just to try and ascertain whether these things are known by you, grade 12, we're going to just give you some few questions that we expect that you'll be able to answer quickly here without even us stopping. The first question will be: define the term oxidation and reduction. Right from the top of your head, you should be able to define that. And the second question would be: explain the difference between an oxidizing and a reducing agent. Can you do that? And the third question that we will ask you, or you should be asking yourself, is: can you define an electrode? What is an electrode? And then name the electrode where oxidation half reaction takes place. The name of that electrode. Now, what is the name of the electrode where oxidation reaction takes place? And then the name of the electrode where reduction half reaction takes place. So these are the things that we expect should be known by you, right? And the answers to the question are as follows. The definition of oxidation, or in differentiating between oxidation and reduction, we say oxidation is the loss of electrons. This is the formal definition of oxidation. And then reduction is gain of electrons. As you can see here, I've highlighted in red O, I, L, and I've also highlighted in red R, I, G, which is oil rig. Okay, oil rig is a name that comes up when you put these alphabets together. They give you a mnemonic called oil rig, which is a mnemonic that we use most of the time to remember the definition of oxidation and reduction. Oil rig, okay, where oil stands for oxidation is loss of electrons. Rig, R-I-G, stands for reduction is the gain of electrons. Excuse me. Right, and then are we able to differentiate between oxidizing agent and reducing agent? Yes. An oxidizing agent is a substance that is reduced. An oxidizing agent is a substance that is reduced. And I think this is where most people start struggling. This is where most of you start struggling, because now I'm saying oxidizing agent, but now I'm saying it is reduced. Now you have to remember, it is undergoing oxidation. Okay, if a substance is undergoing oxidation, then in grade 12, this is just a language. This is a language issue. Something is undergoing oxidation. That is the process that it is undergoing. Okay, but what is happening to that substance? That substance is being oxidized. It is being oxidized. So whatever is happening to that substance, it is being oxidized. It is undergoing oxidation. So when a substance is undergoing oxidation and being oxidized, it cannot be oxidizing itself. So it cannot also be the oxidizing agent. So that's not how it works. It must be oxidized by something. So it is oxidized by the reducing. It is, it is oxidized by the oxidizing agent, but it is the reducing agent. Itself, it's the reducing agent, because it does not do the oxidizing. What the substance does, it gives the electrons. So there's another substance that will be undergoing reduction in grade 12. Okay, that substance that is undergoing reduction, it is undergoing reduction because of substance A. So substance A undergoes oxidation, and then substance A reduces substance B. So substance B is being reduced by what? By substance A. So substance B is an oxidizing agent. it is an oxidizing agent. So you must be able to understand it like that, that if I'm undergoing oxidation, I am being oxidized, but then I'm not oxidizing myself. Therefore, I cannot be an oxidizing agent, right? What I am is a reducing agent because I'm reducing the other guy. The other guy is undergoing reduction, which is caused by me. The other guy is being reduced by me. So I am the reducing agent because I'm reducing the other guy. And the other guy is the oxidizing agent because they are oxidizing me. So this is just a matter of language, grade 12, okay? It's a matter of language. Just come down and understand the language. Oxidation, oxidized, you are a reducing agent then. If you are undergoing oxidation, you are being oxidized, then you are a reducing agent because you cannot be an oxidizing agent. You cannot oxidize yourself. The other substance oxidizes the other substance, while this substance reduces the substance that was oxidizing it. Okay, so it's a matter of just playing with words, a language issue. Okay, all right. Let's carry on with our baseline assessment solutions there. Okay, and then we have anode there being the name of the electrode, and then we also have cathode being the name of the electrode where oxidation takes place. This is where oxidation takes place. Okay, this is where oxidation takes place, and then cathode is where reduction takes place. Okay, these are things that we expect that you must come to the lesson already knowing or at least being familiar with. And if you don't know them, then know them moving forward from today. Cathode is where reduction takes place. Okay, it's the issue of a language. You get used to the terminology, the language. You're going to be fine. The concept itself is not difficult. Maybe the words are new to you, the language is new to you, but that is fine. You will get used to it. The concept itself is not that difficult. You will see whatever is happening here is just sort of general knowledge. You will see great talk. So let's quickly familiarize ourselves with the terminology, some of the words that we are going to be using in this topic. The first one being what we've talked about, oxidation. Oxidation is the loss of electrons. Aldrich, oxidation is the loss of electrons. And then reduction is the gain of electrons. We've said that again. But then an oxidizing agent is a substance that is reduced. A substance that is reduced, that's an oxidizing agent. Okay, it is the substance that undergoes reduction. That's another way you can actually define it. A substance that undergoes reduction. It's an oxidizing agent. Okay, reducing agent is a substance that is oxidized. It's a substance that is oxidized. We say it's a reducing agent. Or you can define it and say a substance that undergoes oxidation. It's a reducing agent because it cannot oxidize itself. Okay. Okay. Then the term electrode, that is a point in an electric circuit where electrons can either enter or they can exit the circuit. Okay. You'll remember that we've spoken about the anode and the cathode of a diode when we were doing electronic properties of matter. So those were the points in a circuit where electrons can either enter or they exit. You remember there was electrons entering then a diode with the creation of that depletion region. You remember all of those things, I'm sure, grade 12. Okay, so we say an electrode, that is just a point in an electric circuit where electrons can enter or exit the circuit. Okay, the most important thing is you knowing electrodes and identifying them in this case. And then we have anode. An anode, that is the electrode where oxidation takes place. Again, we've said this. Anode is the electrode where oxidation takes place. And then a cathode, that is the electrode where reduction takes place. So these are names of the electrodes. Name of the electrode is the anode. The name of the electrode is the cathode, grade 12. As we continue with our terminology, galvanic or voltaic cell, right? This is when we define the cell that we're going to be dealing with for the day. It's an electrochemical cell that converts chemical energy to electrical energy. This is where the exciting part happens. Here in a galvanic cell, grade 12, we are going from chemical energy. So we are using chemicals. We're saying chemicals, can we put you together such that you create electricity for us? That's what is going to happen. We take the chemicals, they are converted to what? to electrical energy. So the energy conversion that takes place in a galvanic cell is that of a chemical energy being converted to electrical energy. We get electricity from chemicals. That's the idea behind the galvanic cell. We get electricity by using chemicals, okay? Spontaneous reaction. This is a reaction that does not require energy or external energy to drive the reaction. This reaction happens all on its own, automatically, without having external energy or a power source that is going to drive this reaction such that it occurs. This reaction is just going to, as long as you put these chemicals together, just going to react on their own without anyone pushing them or anything pushing them to react. So we say that reaction that occurs like that is a spontaneous reaction. A very important word there. And then lastly, let's look at the term electrolyte. What is an electrolyte? This is a solution that conducts electricity through the movement of ions. So you have a solution there, and then you're going to have ions, obviously, in that solution, and then the solution helps you to conduct electricity. So that solution, we call it an electrolyte. Right. Those are the terms that we are going to be using. You will hear me talking about all those terms: electrode, electrolyte, this and that, all these terms that I've mentioned here. So again, don't worry, we'll get used to the terms, but the concept itself, you would find that it's not that difficult. Right, grade 12, let's get into it now. Let's talk about this galvanic cell. Okay, as I've said to you, this is a nice thing, a topic for me. I like it because this topic is talking about electricity. It's talking about something that I can actually see happening. I can see the electricity. How is it that this electricity occurs? And here they're talking about generating electricity from chemicals. So they are saying from chemicals, you can have electricity being formed. Again, so galvanic cell or voltaic cell, again, the definition is it is an electrochemical cell. And what does it do? It converts chemical energy to electrical energy. So that's what a galvanic cell, it converts, as you can see in the picture that I have here. Here are the chemicals, and these chemicals, they will turn and they will give you electricity, as you can see here. So what's the idea behind the galvanic cell? So I'm going to paint like sort of a basic idea of what is actually happening in a galvanic cell. So here's what is happening. So in a galvanic cell, the idea is that if you have maybe a certain metal, right, call this metal P, okay, then this metal, and you put it next to another metal, which is Q, right? And then you find, this is what was happening, and this is how I think they discovered the galvanic cell. They can see that every time you put P next to Q, P tends to take electrons from itself and it gives them to Q. It happens naturally, spontaneously, without anyone pushing it to happen, right? For example, if you have zinc metal and you put it outside or you put it in water, or nail, all right, your nails, which are made up of iron, you put them in water. After some time, and I'm talking about nails that are not galvanized, by the way, after some time you find that these nails are rusting. What is happening there? The nails are losing electrons, and they are losing electrons, and it's going to oxygen. So there are certain substances that happen or do that in natural life, in the real world, okay? There are certain substances that when you take this substance and you put it next to another substance, probably in a moist environment, or there's some electrolyte that is there, that one of those substances will always give electrons to another, or the other one will take electrons, okay? Either the other one is giving or the other one is taking, but at the end of the day, electrons will move from one substance to another substance, okay? So that's the idea behind the galvanic cell. So I'm thinking these people said, okay, we can take advantage of this situation. How about I take P, right? Substance P, then I separate it with substance what? Q. But then I offer, because I know P wants to give electrons to Q. I know this is going to happen. Then how about I offer a pathway like a conductor, right? And then I say, yes, P, you want to give electrons to Q. So I will offer the pathway for the electrons to move from P to Q. And here are the electrons moving from P to Q. But then along the way, I will take advantage of these electrons and then I will put a bulb along the way of the path that I offered for the electrons. Then that means I am taking advantage of the flowing of the electrons. And what is the flowing of the electrons? That is electricity, grade 12. Electricity is the flow of charges, or it's electric current at least. So those flow of charges is electricity. So these people said, we can take advantage of this spontaneous reaction that is happening, where we know that P will always give electrons to Q. I hope you understand my story there, and I hope you find it as exciting as I do. I know that P will always give electrons to Q, right? Then what can I do? Let me separate P and Q and then offer them a pathway for the electrons to flow from P going to Q. But I know my plan. My plan is that along the way, while the electrons are going from P to Q, I am going to use them. And that is how we actually get the cell of your cell or the battery of your phone, of a phone. You know that you have a phone. I'm having a tablet, writing on a tablet right now. It's not connected to some power source. That means there must be a cell. And how does that cell function? It functions through or it is a galvanic cell. We can actually say that cell is a galvanic cell, and it works like that. There is a substance that is busy giving electrons to another substance here, but along the way, while it is doing that, I take advantage of that through the using of this tablet that is in front of me. You do the same thing with your phones. As you are busy watching me there, you are doing that, taking advantage of that. Okay, so that's the idea. That's the conversion of the chemical, because we know that there was going to be a chemical reaction happening between P and Q. But now we want to convert that chemical reaction into what? Electrical energy, or chemical energy into what? Electrical energy, where the electrons are now flowing, that we take advantage of that. But now we cannot or we don't see in the battery it looking like this. So this is the basic representation of a galvanic cell. Grade 12, one where we can perform in a lab. Okay, we can perform the galvanic cell or the experiment in a lab. This would be the basic representation of it. And how does it go? Very, very important for us to know. A galvanic cell is always going to have two beakers. So that will be beaker number 1, and this will be beaker number 2. Very, very important. Okay, it can either be beaker 1, beaker 2. The issue of numbers does not matter, but it's important that in a galvanic cell, you know, there will always be what? 2 beakers. Okay, that's if you have your galvanic cell in a laboratory or you are being asked question in an exam. Okay, then inside this galvanic cell or these beakers, we then put these metals. These are the metals that are going to now lose electrons and gain electrons, depending on who tends to take and who tends to receive. You would remember that there was that discussion in grade 10. Okay, so these ones, we call them electrodes. This is the point where electrons will either enter or they will exit in our circuit. So we call them what? Electrodes. So these are electrodes. So there's electrode 1 and electrode 2. Okay, then these electrons are going to be submerged in this solution, and there's going to be a solution there. What do we call this solution? The solution is called an electrolyte. So each and every electrolyte will have its formula, okay, right? The electrolyte, what forms that actual electrolyte, okay, right? And then outside here is going to be your appliance. That appliance can be a bulb. Usually they use a bulb, or it can actually be, sometimes they use a voltmeter, right? A voltmeter shows that there's potential difference, and if there's potential difference, then there must be electricity flowing there, or charges or electrons, okay? And then this direction shows that the electrons are flowing, so that will be the flow of electrons, okay? And then you now have, obviously here, this is what? This is a conductor. This is the path that is being offered, because we know that this electrode will give electrons to this electrode if we were to put them together. So then we have decided to separate them and then offer a pathway through a conductor. So to say, yes, you want to give electrons to this one. How about you give them through this wire? We want you to give them through this wire so that along the way, we take advantage of it, then we get light and we have electricity. Beautiful stuff to me there, grade 12. And then you have this instrument there. This one here, this U-shaped thing, we call it a salt bridge. We call this U-shaped thing, it is a salt bridge, okay? We're going to talk about the functions of the salt bridge, what it does, and all of that. And then these arrows are showing the movement of ions in the salt bridge, things that we are going to talk about, okay? Before I move on, I want to quickly recap here. This is a galvanic cell. I want you to know all of these components of the galvanic cell. You must know that the galvanic cell has two beakers. You must know that the galvanic cell is going to have electrodes. You must know that the galvanic cell is going to have electrolytes. Okay? You must know that the galvanic cell is going to have a conductor and a bulb or a voltmeter or even an appliance. You must know that the galvanic cell is going to have a salt bridge. These are things that separate a galvanic cell from other cells that we are not going to be talking about, at least for today. Okay? It separates them from itself from other cells. Okay? Two beakers, salt bridge, appliance, bulb, voltmeter, conductors, electrolytes, and electrodes. Okay? Maybe other cells, they do have electrodes and electrolytes, but only a galvanic cell for ourselves, only a galvanic cell is going to have a salt bridge. Only a galvanic cell is going to have the bulb or a voltmeter. Okay? So that's a galvanic cell. All right? Now, one part of the electrode or one side of the electrode is going to be negatively charged, and the other one is going to be positively charged. Okay? Then we'll talk about the name of the one that is negatively charged and the other one that is positively charged or is positive. Okay? So what I want us to do now is to sort of dive deep down into a microscopic view of what actually happens in a galvanic cell. Maybe this is going to give you a better understanding and you understand the galvanic cell. Okay, so let's say I have a cell like this one. I'm going to go for the most popular one, which is the zinc and copper cell. The zinc and copper cell. So what's the idea here? The idea is to convert chemical energy into electrical energy. What do we know? We know that zinc tends to give electrons to copper. Let's say we know that for now, because we'll talk about how you predict later on. Let's say you know that, okay? We know that zinc tends to give electrons to copper, okay? Now, how everything happens at microscopic level is very, very important. So let's zoom in to that zinc there, grade 12, and say this zinc actually is made up of very, very tiny zinc atoms that make up the zinc metal, okay? Then you have the copper that is made up of extremely tiny copper atoms as well. All right. Then inside here you have a solution of a zinc sulfate, ZnSO4. Right. And then here you also have a solution of copper sulfate, CuSO4. So what happens? Firstly, in your solution, what is going to happen is that these people are going to separate. Okay, they will ionize. Okay, so in your solution, when you put them in water and you stir, they are going to separate, and then they will separate into their ions. Meaning inside here, I'm going to have the Zn2 plus as already have been indicated. Let me do another one, Zn2 plus, and I will also have the SO42 minus, SO42 minus, SO42 minus ions. And as you can see, they are balanced. For each Zn2 plus, they said SO42 minus. So, but the issue now here is that they have been separated. They are no longer one compound. The same thing will happen here. We'll have the Cu2 plus, okay, and then the SO42 minus, the SO42 minus, and then the SO42 minus, the sulfates, okay. As you can see again, balance. For each Cu2 plus, there's an SO42 minus. Okay, for each Cu2 plus, there's an SO42 minus. They're balanced, but they're separated. Okay, they're going to become important, right? So then what happens here? What happens here, grade 12, is that this zinc will start then losing electrons, because zinc will lose electrons. It tends to lose electrons when it is next to copper. Okay, so this one zinc will lose an electron. Let's take this one here. It loses 2 electrons. Then these 2 electrons, they start moving, right? The 2 electrons, they start moving through the conductor that we say we are offering a pathway through the conductor, okay? And then when this zinc electrons loses the electrons, it then becomes a zinc 2 plus. Why? Because it lost 2 electrons. Remember in grade 10, we talked about this. If an atom loses electrons, it becomes positively charged, okay? And the charge will depend on the number of electrons that it lost. So if it loses 2 electrons, it becomes 2 plus. So what do we know here? We have a zinc, right? That has turned to become zinc 2 plus. Why did the zinc become 2 plus? Because it lost 2 electrons. Already we have been able to write the oxidation half reaction. But let's continue, okay? Let's say this one also loses the 2 electrons. Again, the same thing is going to happen. The zinc 2 plus falls into the solution while the 2 electrons move through the wire going to the other side. And while they're moving through the wire, they find my bulb, they give me light, they continue moving to the other side. I have light, I am good. There is still something that is happening there inside. What is happening inside? When these electrons come in here, right, they reach this side. Remember, these electrons are finding the copper here, which is neutral, because this one is neutral, right? There's no charge, as you can see. They come in here, they are negatively charged. When they come in here negatively charged, they will then attract the what? The copper 2 plus ions, which are positively charged. Remember, opposite charges will attract each other. They then attract them. These copper 2 plus will find themselves going here to meet those electrons that are coming from zinc. So the copper 2 plus, they actually accept these 2 electrons coming from zinc. I want to emphasize here, it is the copper 2 plus that accepts the electrons, not the copper. The copper is neutral, it's fine, but the copper 2 plus ions are the ones from the solution itself, are the ones that will do what? Go and accept the 2 electrons that have been sent by a zinc metal. Therefore, when it accepts the electrons, then the situation becomes like this. You had a copper 2 plus accepting 2 electrons, then it becomes what? It becomes a copper, because now it becomes, remember, it was 2 plus, meaning it was missing 2 electrons to be neutral. Now it gains the 2 electrons from zinc. It will now then become a what? A Cu, a copper, attaching itself around that copper electrode. So this copper 2 plus no longer exists. Okay, the same thing will happen with this copper 2 plus. It will accept the other 2 electrons that were sent by another zinc atom. Then it becomes what? Cu. This copper 2 plus no longer exists. Okay, so what is happening here? A zinc turned into a zinc 2 plus. Why? Because it lost 2 electrons. That's what happens then. Just by that, we can identify and say, well, since losing is happening here, oxidation is taking place here. And this is the reaction that we can write to represent the oxidation half reaction. And here there was a gaining that was happening. So that means here reduction is taking place. And if reduction is taking place, we can say this one is being reduced. If it is being reduced, itself cannot be a reducing agent. No. It is being reduced by what? It is being reduced by the zinc, the Zn. So itself, it is the oxidizing agent, because itself is the one that is causing the oxidation on the other side. I hope you are now getting used to the terminology. The Cu2 plus causes the oxidation here. So this one is undergoing oxidation. So it is correct to say it is oxidized. But it is not correct to say it is an oxidizing agent. No, zinc is not an oxidizing agent. Zinc does not cause oxidation to no one. Zinc causes a reduction to the other person. So zinc is a reducing agent because it causes reduction to the other side. Get used to the terminology, please, grade 12. It's going to help you, okay? Right. Now, as we go further into this, what you would realize is that now we have lost this copper. We have also lost this copper, okay? This side in the solution. I want us to go to the solution now in the electrolyte. What is happening in the electrolyte? Because we've written the half reactions and the story that is happening there. We have taken advantage, and I hope you are with me there.
In this solution here, we no longer have the Cu2 plus, we no longer have the Cu2 plus because they've become copper, or they've become copper. Here, we now have the Zn2 plus and now have the Zn2 plus. So this right here, grade 12, is a problem. Okay? Why is this a problem? All right. This is a problem because, remember, I said for every Zn, there's an SO42 minus. For every Zn, there's an SO42 minus. This is what I said. But now these new Zn2 plus that have come in here have caused that they are now more Zn2 plus than the SO42 minus. I hope you can see that. So that's an issue. That's a problem there. There's an imbalance on this side of cell. Okay, when you go to the other side, you check the Cu2 pluses have been cancelled. Now I'm only left with what? One Cu2 plus, but I'm left with 3 SO42 minus. So again, this side as well, there is an imbalance of what? Of the negatively charged ions, or the negatively charged ions are more. So we say this side, there is a build up of positive charges. Okay, I hope again, grade 12, I hope you're with me there, and I hope you're not getting confused. There's a build up of the positive charges here. What is causing the build up of the positive charges? It's because the zinc are going from being zinc to being Zn2 plus, or zinc 2 plus, the ions. So they are going from being atoms to being ions because they are losing the electrons. The oxidation up reaction actually tells the story if you follow it, grade 12. The zinc atom loses 2 electrons, or becomes zinc 2 plus, because it loses 2 electrons. That's why the zinc ions are falling into the solution, and more Zn2 plus are falling into the solution, and there are no SO42 minus to match them. Therefore, we are building up the positive charges this side. Okay, go to the other side. The Cu2 plus ions are taking these electrons that were lost by the zinc, and then more and more of them are taking the electrons, leaving the SO42 minus without partners. Remember, they were partnering. Then here we are actually building up. So there's a build-up of a negative charge. There's a build-up of negative charges this side. So one cell will have a build-up of a negative charge. One cell will have a build-up of a positive charge. That's a problem, okay? And if there's that build-up and there's no imbalance, the circuit is not going to function. So as it is right now, our circuit is not working, grade 12, okay? Okay, here's another reason why our circuit is not working. If you can see, our circuit starts, electrons start flowing from here, and then they go through here, then they end here. There is no circuit that looks like this, grade 12, okay? There is no circuit. Even if we said we had a battery, or our battery was starting here, there is no circuit that looks like this. A circuit must be a closed loop. Hope you remember that. A circuit must be a closed loop, so that there is what? There is no gap. Once the circuit has a gap, then the circuit is incomplete, then the circuit cannot work. So the circuit must be a closed loop. So we have two problems here that is causing our circuit not to work. One, there's a gap here. Between these two cells, as you can see, there's a gap. Nothing connects this side to this side. There's no connection from here to here, grade 12. There's a gap. And if there's a gap, our circuit is incomplete. Right? For the circuit to function, the circuit must be complete. Number two, while these electrons are moving, there has been a buildup of positive charges this side and a buildup of negative charges on the other side. And those buildup are causing the electrons to actually stop moving. Okay? So how can we solve this issue? Comes in this thing that we talked about. We put in a U-shaped thing, right? And this U-shaped thing is called what? A salt bridge. This U-shaped thing is called a salt bridge. Very, very important thing. Let's talk about the name again. Salt bridge. It's a bridge. What does a bridge do? It helps you go from one side to the other side. Okay? So what is this bridge doing? It helps salt go from one side to the other side. Okay? There are different types of salt, by the way. Okay? So for example, I could just simply take NaCl, which is a type of salt, right? Make a solution of it and then I'll put it in water to make a solution of it, obviously, so that it ionizes. You must do that for the ions to move, okay? Then you put it here while it's in the form of a solution, it has ionized, the NaCl, okay? So let's try and do it here so that maybe you can see I have enough space. Here's my salt bridge, all right? Forgive my drawing there. My salt bridge is supposed to actually end here. Forget this part. It's not part of my salt bridge. So inside the salt bridge, I'll put in the NaCl, but an ionized one, meaning that it has been put in at least water, right? So that it ionizes. It has been put at least in water so that it's going to ionize. I cannot just put a salt in its solid form. If I do that, this thing is not going to work. I must put it such that it is ionized so that I have the Na plus ions and the Cl minus ions, okay? Obviously, there will be more. I'm just representing one, okay? What is the function of these ions? The function of these ions is that they must now go. First, the salt bridge, what it has done for me, it has then completed that gap or closed that gap. So I can say it has completed the circuit, okay? So why did I put in the salt bridge? There was a gap between my what? My beakers. And then the circuit was not complete. So then what did I do? I introduced the salt bridge so that it completes the circuit. A circuit must be complete for it to function. Number two, in the salt bridge, to then solve the issue of positive and negative buildup, in the salt bridge itself, I put in salt. I put in salt such as NaCl, sometimes it will be KNO3, potassium nitrate there. Whatever the salt may be, it's put in there, it ionizes, okay? After it ionizes, then this is what is going to happen. Remember, there was a buildup of a positive charge here. I will have negative charges here from the salt bridge actually moving to the side where there's a buildup of a positive charge. And what are they going to do there? They are maintaining neutrality. Okay, they are made so that it becomes neutral again, because remember it was neutral before there was a buildup. It was neutral. For every SO4 there was a ZN2 plus. I hope you get me. So this Cl will come here to then maintain that neutrality. Let's have that neutrality again, while the Na plus ions will move to this side so that we can have again this side neutrality, because here we're having more negative charges than the positive charges. So let's put in the positive charges such that the positive charges are going there to balance and neutralize. Okay, so right then and then, I'm just giving you the why, the salt bridge, and why we have it, and even its function, so that when you're being asked the functions of the salt bridge, you are ready for it. You know that the salt bridge functions like this and this. Okay, so one, it will complete our circuit. Number two, it will then allow or it will then maintain electrical neutrality. That's how we actually put it. It will go there to maintain the neutrality between the beakers. Okay, so at basic rate, you can say, or at microscopic level, this is what is actually happened in a galvanic cell, right? So I'm going to move on now, and then I'm going to move to what you're most interested into, to say, how do you answer questions? Maybe you're not interested in what happens here, but I think it gives a better understanding of the cell and why do we need certain things in a cell. Okay, but let's move on and look at the functions of a salt bridge summarized now. Okay, what are the functions of the salt bridge? Very, very important points for you to take there. Always, first thing, the salt bridge is there to complete the circuit. We cannot have a circuit that has a gap. Okay, the circuit must be a closed loop. Obviously, in our usual circuit, there is a source of energy, but at the end of the day, a circuit must be a closed loop. There is no gap in between. Number two, you remember, there's a buildup of a positive charge, and then there's a buildup of a negative charge. Then the circuit is there to maintain, or not the circuit, but the salt bridge is there to maintain electrical neutrality. It maintains that neutrality. Without that neutrality, there will be no flow of electrons, or there will be no chemical energy converted to electrical energy. And number 3, if asked for, most of the time they asked for 2. Most of the time they will ask you for 2, grade 12. But if they do ask for 3, I feel like this one sort of says the same thing as the second one, but I'll put it anyway. Allows for movement of ions. Okay, this another one, allows for the movement of ions. Me personally, I think number 3 says the same thing as number 2, which is why I think the examiner usually asks for 2. Okay, let's go back a bit and then talk about observation. If you were to perform this experiment in the lab, okay, what observation will you make? Well, obviously you will make an observation. In that case, you will use you can use an LED, okay, very sensitive one, right? It will work. Or you can use a voltmeter. Obviously you would observe that there will be potential difference. Okay, that's what you will observe. There will be potential difference. Okay, but number 2, what you will also observe here, then after some time you will observe that if we keep on losing the Zn and they are falling into the solution as Zn2 plus because they've lost electrons, then here there will be a loss of mass. Very, very important observation to talk about here. See, this side here, there will be a loss of what? Of mass. And this side here, there will be a gain of mass. Remember, the copper ions, they keep on attaching themselves then. Okay, fine. And then remember, we say these are electrodes. Okay, point where electrons are exiting or point where electrons are entering the circuit. So these are the electrodes. What is the name of this electrode? The name of this electrode is called the what? The anode. Okay, the anion electrode. Anode, ion or anion electrode. That's where the word anode comes from. And it's going to be a negative electrode. This is a negative electrode because anions are negative. Okay, and this one is called a what? Is called a cathode. Okay, a cathode from cations electrode. Cations electrode or cations electrode. That's where you're going to have your cations. That's right. And the cathode is going to be positive because cations are positive. Then that's another thing that is very, very important for you to understand. And without causing confusion, I want us to talk about the agents now. Then I will move on to how you answer questions then. Let's talk about the agent. So it is very, very important for you to be specific when you're talking agents and look as to exactly which substance is losing the electrons or which substance is gaining the electrons. Okay, so if someone was to ask for the reducing agent, which substance is the reducing agent? Which substance here is losing the electrons? Okay, is it the zinc? Is it the zinc 2 plus? Is it the FO2 minus? The actual substance that loses electrons, I hope you are saying with me, it's the zinc. Okay, or Zn. So zinc is the reducing agent. Okay, but let's go on the other side, the oxidizing agent. Which substance actually gains the electrons? Most of you grade 12, you rush and say copper gains electrons here. Copper does not gain electrons in this case. It's not actual copper here. Here's the substances that are here. There's a copper atom, okay? There's a copper ion. There was a copper ion and then there's a sulfate ion, okay? So which one is actually gaining the electrons? The one that is gaining the electron, it is the copper ion. The Cu2 plus is the oxidizing agent there. Cu2 plus, the oxidizing agent. I hope this helps in terms of how you identify the agents. Grade 12. Be specific. Don't just be general and thinking copper gains, copper gains. It's not actually the copper that is gaining, but it's the copper ion. And this is where most of you will be losing marks, where they are asking for the reducing agent and for the oxidizing agent. Grade 12, this is what is happening at microscopic level in a galvanic cell. And I hope it brings maybe a different picture. I hope it gives a more understanding of the galvanic cell itself. Okay, we've talked about the functions of the salt bridge. Okay, let's look at how you predict everything that I've just done just by using the table of standard reduction potential. There's also a table of standard reduction potential. There's an easy method that most people will call the Z method. Then I'm pretty sure most of you are familiar with. Okay, so how will we predict? Well, we have two beakers there, if you remember, and one beaker has a zinc, and then the other one has a copper, and then there is a light bulb maybe, and then let's say it was complete with a salt bridge. Then you can identify, oh, this is the galvanic cell. Okay, now how do I identify firstly the oxidation between zinc and copper? Which one is undergoing oxidation, which one is undergoing reduction? I go to my standard reduction table, right? There are two tables, okay? Table 4A and table 4B. They are actually the same table, it's just that table 4B is the flip of table 4A. So what was on top on table 4A is at the bottom in table 4B, right? For galvanic cell, I use table 4B with most learners. And if you are going to use this method that I'm going to use, you're going to have to use table 4B for this one. If you use table 4A and you use the Z method, you're going to have a problem. You're going to get incorrect answers. So please, if you are going to stick to this Z method, use table 4B for galvanic cell. For galvanic cell, I repeat. Right. So what do? We say we have a zinc metal, we have a copper metal. Let's go and identify zinc, right? Or copper. Which one we check first, right? We find zinc. Here is zinc. Here is zinc. Hope you can see it with me there. And then we go and look for copper. Okay, here's the first copper. And then here's the second copper. And then there's also another third copper. Then there's an issue of saying which copper do we choose? Okay, which copper we choose will depend on our electrolyte. Okay, if our electrolyte is the copper 2+, right, then we'll go for this copper 2+ here. Depends on the electrolyte. So the electrolyte will always be there to tell you which copper you choose. Grade 12 then. So the copper electrolyte, we cannot choose this one, for example, because this one does not completely turn to copper. You can see it is copper 2+ gaining an electron, but it does not completely turn into copper. But here we are having a situation where it completely turns into copper, so this one is out. We cannot choose this one because this one is a Cu+, meaning that it's only one electron gained there. It gains only one electron. What we need is the one that will gain 2 electrons. Or in the electrolyte we had CuSO4. When that ionizes, it ionizes to Cu2+. So definitely this one is out. Okay, then what do we do then? Let's rewrite that reaction. We'll write Zn 2+. Okay, and then it's written like this in the table. Okay, so there are certain things that you need to be careful of when you are using the table, grade 12, right? Then let's write the copper, Cu 2+ plus 2E. If you notice, both of these reactions are written in the same format, and that's the format of reduction, hence it's called the standard reduction potential. So what you will do is you quickly go there and draw your Z and put arrows on your Z. What are these arrows there to do? They are there to help you identify the arrow that you should put, because you can never write this reaction with double arrows and get correct or get marks there, grade 12. So be careful. So here you are supposed to pick the one arrow. So the Z helps you. So you write the one on top, you write the one at the bottom, then you draw your Z with the arrows. The arrows are telling you pick the arrow going that direction, and this one is telling you pick the arrow going in that direction. Then you should be fine. If you are asked to write the oxidation half reaction, you will then write Zn 2+ plus 2E. Then I am going to pick this arrow and it gives me Zn. If you have written it like this, you're 100% correct to get your full marks, grade 12. However, here's what I always advise people. I say, after you have written like this, just flip it. It shouldn't be too difficult. Just flip it and write the mirror image of it. Then it will be actually Zn, flip the arrow, then write Zn 2+, then write 2E. Once it has been flipped like that, it helps when we have to write the net ionic reaction. You will see, right? So we have written it like this. But if you want to leave it like this, you are still fine, you will get your full marks. But this will get you no marks at all. Be careful, right? Then it's time to write the reduction half reaction. The reduction half reaction, that tells me that I must pick this arrow going in that direction. So Cu2 plus 2E, and then this arrow I am picking turns into Cu. Then I'm done. Okay? Right. How do I know that the one on top is undergoing oxidation, that the one at the bottom is undergoing reduction? Well, you can memorize that if you want to. The one on top always undergoes oxidation. The one at the bottom always undergoes reduction, right? You can memorize that using table 4b, I repeat. Or you can just simply look at these arrows. They are telling you here, as we go up, we are increasing reducing ability. Remember, we said the one that is undergoing oxidation is oxidized. It is the reducing agent. So when you compare between the two, the one on top will have a higher ability to be a reducing agent than the one at the bottom. So that's how we actually know. But if you want to memorize, you can just simply memorize it like this. The one on top will always undergo oxidation. The one at the bottom will always undergo reduction. But there's a scientific reason for it based on the table. That's how you know. So, okay. Now, let's talk the net reaction. If they ask us to write the net ionic reaction, what do? Once you have written it like this, make sure that you have electrons one side and electrons on the other side. You simply go to your reactions and then you will cancel the electrons. These electrons will cancel. And then you see top plus bottom, arrow, top plus bottom. Then you're done. That's your net ionic reaction. 3 marks is what they usually give for this question. 3 marks for the net ionic reaction. Free marks. If you are able to write your oxidation half reaction, you are able to write your reduction half reaction, then you should be able to write your net ionic reaction. This is how we do it when we are using the table. And the table is pretty much easier to use, I have to say. Right? Before then, I was just giving you a microscopic view of it and a better maybe understanding scientifically of what is actually happening there. Okay? Let's move on then. Let's take an activity for about 3 minutes, grade 12, where I want to check if people can actually identify oxidation and the reduction there. So your activity starts now. Welcome back, Rachel. I hope you are done with your activity. I gave you an actually simple activity so that you can do it quickly and we save time for more explanations. All right. So our activity goes as follows. From the cell above, write down the following. Right? There's a cell that you've been given. We want you to identify or the electrode that undergoes oxidation. So identify the electrode that undergoes oxidation and state whether the electrode is the anode or is an anode or a cathode. All right. And then the electrode that undergoes reduction and state whether it is an anode or a cathode. Very, very simple. But the issue here is the identification. Can you identify? Can you use the table 4b to identify? It's a very, very important skill there. So you can see here, what is being compared is tin versus cadmium here, right? So tin versus cadmium here, which one will undergo oxidation, which one will undergo reduction between the two? Very, very important. Look at your electrolyte here. This is your electrolyte here. It's the Sn2 plus. This is important. The Cd2 plus. The ions. They are important in telling you which tin you are going to choose and which cadmium you are going to choose when you get to the table 4b, because you can find that it might be more than one. This is the question that maybe most of you might be asking. How do I choose? How do I know which one to choose? Okay, the electrolyte, let the electrolyte tell you which one to choose. Okay, right. So let's try and check there what should be the answer. The answer should be the cadmium is undergoing oxidation and its name there is the anode. And the tin is undergoing the reduction and the name is the cathode. How do we know? Table 4b, we look for cadmium. Okay, where is the cadmium? You look for it, you should find it here. And it is the Cd2 plus. Here it is. Okay, now once I find the tin underneath it, definitely the cadmium is undergoing oxidation. That's what we said, okay? So, because it has a greater reducing ability. If you're being asked to explain, it has a greater reducing ability. Then let's look for tin. Here is tin, right in the bottom there. Yeah, the Sn2 plus one, okay? We choose the correct one, not the Sn4 plus. You saw the electrolyte in the question, it was 2 plus. So you cannot come and choose this one. Okay, so it's very, very important to choose the correct one. Here is the Sn2 plus. So what you will do here, if they were asking you to write the reaction and all of that, that's when you will come here and draw your set with your arrows. Then you will write the oxidation, the reduction. But for the mere fact that it's on top there, the Cd, then it is undergoing oxidation. And the Sn or the tin is at the bottom. It must be undergoing reduction. And the electrode where oxidation happens is called the anode. And the electrode where reduction happens is called the cathode. Simple as that. The issue of identifying. It's a very important skill there. Okay. So without any further waste of time, let's continue. Right? Okay. So grade 12. This cell, if you are performing it in a lab, you might find that you don't actually find the values. You don't actually find the values that are theoretical values. And why is that? It's because this cell, for you to find those theoretical values, must be performed under what we call standard conditions. So there are conditions that must be met for the cell to give you those theoretical values for the standard reduction potential. Okay, and what are those conditions? One, your electrolyte must have a concentration of 1 mole per decicubic meter. That's number one. And if you write these conditions, you write the whole thing in full. Don't just say concentration. It's concentration of 1 mole per decicubic meter. Write the whole thing. And number two, the temperature must be of 298 kelvins. From grade 10 and even grade 11, you'd remember that 298 kelvins is the same as 25 degrees Celsius. I should have written Celsius here, right? Okay, 298 Kelvin, 25 degrees Celsius. So you can choose one of the numbers to use. If you're going to stick to 25, stick to 25. If you stick to 298, stick to 298. Choose one, stick to it. No need for you to confuse yourself between the two. Okay, these are the ones that are mostly going to be the one that you must meet in most of the galvanic cells. In most of the galvanic cells, you must meet the issue of 1 mole per decicubic meter concentration and the issue of temperature of 298 kelvins. Okay, Now, the third one must be a condition that is met if we are dealing with gases. If one of the electrodes is a gas, then you can talk about the third one. So I'm saying to you, if you're being asked for these conditions, the first two conditions that you must always consider, grade 12, is the concentration condition, and it is also the temperature condition. Those are the first two. Then you can talk about the what? The pressure if you have gases. Or if they ask you for conditions in general, then they ask for three again. Then you can talk about the pressure of 1 atmospheric pressure or 101.3 kilopascals. So those are the conditions. And mnemonic to remember them, I usually use the abbreviation of Cape Town City, CPT, Cape Town. Cape Town, the Cape Town City, okay, one of the biggest cities in South Africa. Cape Town is abbreviated using the letter CPT, where C can stand for concentration of 1 mole per decicubic meter. P stands for pressure of 1 atmospheric pressure or 1.3 kilopascals. And the T stands for the temperature of 298 kelvins. But the order of stating them, concentration, temperature, then pressure. That should be the order, okay? Right. Next, the writing of a cell notation. One of the easiest things to do once you understand your galvanic cell. How do we write a cell notation? First thing, draw double lines, right? Then have a line, space here, a line, and have a space here and have a line, okay? So the cell notation's job, grade 12, is to tell a story of what happens, a full complete story, like the net ionic reaction. That's what a net ionic reaction actually does, but there was no time for me to just go into detail of that. But the net ionic reaction tells the full story of what has happened, okay, because it's the full thing. So that's what the cell notation does as well. It tells you that we had this beaker, and then in this beaker, we had this electrode. This electrode lost electrons and it became this, and then these ions took the electrons and they became this. That's what happened. This is what actually happened, okay? Okay, let me show you so that maybe you understand better. What we had was a zinc electrode. We had a zinc electrode. What happened to the zinc electrode? The zinc electrode turned into zinc 2 plus, and it fell into a solution of 1 mole per decicubic meter. This must be written as well, but this is not that important. If you don't write this, you will get your full marks. So it's not that important to write the concentration here. I just like it, okay? Right, so zinc became zinc 2 plus. Again, there's a story here. Zinc became zinc 2 plus, right? Then it became zinc 2 plus because it lost the electrons, but there's no need for us to represent those electrons here, okay? Became zinc 2 plus because it lost the electrons. Where did those electrons go? Those electrons were received by what? There was a Cu2 plus, which was in a solution of 1 mole per decicubic meter. I actually like the putting of the concentration. Now, Cu2 plus was in that solution. It actually accepted those electrons, and then it became Cu. That's the notation right there in front of you, grade 12. Easy stuff. A story that is happening in my galvanic cell. I had a zinc atom losing electrons, becoming a zinc ion, a zinc 2 plus ion. Then I had a copper ion receiving those 2 electrons, becoming a copper, a metal. Again, this again emphasizes the point of saying we cannot then say copper is the oxidizing agent, because copper does not gain. The person who takes the electrons is the what? Is the copper ion. So this is the oxidizing agent. But here, this one is the reducing agent, okay? So these lines are important, all right? And then I know some of you have this, you write it like this, where you say here, it's the anode, and then here you write the electrode, and then here you write the electrolyte, and then here you write electrolyte, and then you write cathode. Notice that way of writing. What you must avoid doing is turning it into a table where you do it like this. This is now incorrect, grade 12, okay? So please, it just must be a line, double line, a line. Where this double line is actually important. It represents a salt bridge. This double line actually represents a salt bridge. So there's a question that could be asked. what does this double line represent? It's a salt bridge. So this is how you write a salt notation, grade 12. And the salt notation, what it actually does, it gives a full story. And that is why I started with the conditions, because one of the conditions is needed when you write a salt notation, the 1 mole per decicubic meters, but it's not necessary. I know that some teachers would say don't write it, and that's correct as well. Okay, so that's how you would write a salt notation. Right. Now let's look into calculating the EMF of a standard galvanic cell using the standard reduction table. We're going to use the same cell that we've been using, the zinc copper cell. Okay, so another easy thing that we do, we calculate the standard or the EMF using the standard reduction table. So how do we do that? A formula is needed. So just go for the formula. That will be my advice to you. And the formula goes as follows. And E naught then is equals to E naught cathode minus E naught anode. Okay, this cathode could be E naught reduction minus E naught oxidation. Okay, it could also be E naught oxidizing agent minus E naught reducing agent. You will see in the formula sheet there will be that formula. What you must never do is abbreviate these things. Okay, don't write your E naught cat, E naught an. Don't do that. Right? Do not abbreviate. In the formula sheet, it's written in full. You must also write it in full. Do not write E naught ox here and then E naught red or red. Don't do that. Okay? Don't abbreviate the thing. Write the formula in full to ensure that you get your marks. Please, grade 12. Right? So then now you say, I have identified long ago the substance that is undergoing oxidation and the substance that is undergoing reduction. All right, so let's do the first one, or we'll do two in actual fact. The first one that we do is the zinc. That means we have to look for the zinc and look for the standard reduction potential of zinc, which is here. It's a negative 0.67. Also look for copper. Where's the copper that we chose? This was the copper that we chose with a 0.34. A positive 0.34. Which one was the cathode? The one undergoing reduction, the one at the bottom. So it's the cathode. So we start with that number. We say plus 0.34 minus, then we open a bracket, because this one is also come with its a sign, which is negative 0.76. Then we go straight to our calculator there. We put it in our calculator exactly as it is. 0.34 minus, open bracket, a negative 0.76, close the bracket. You will get that your answer that you are getting is 1.1 volts. SI unit. People, you forget SI units when you're doing chemistry, and I do not understand why. You are still calculating, there must be an SI unit. And the SI unit there is going to be volt, because what we are calculating here is EMF. And we've spoken about EMF a little bit in grade 11 then, that it is also potential difference, also in grade 12. Right, but the point that we're trying to make here, the answer that we are getting in grade 12 is positive, as you notice here. That is significant. Okay, a positive answer is significant. A positive answer tells us something. If I calculated my EMF here, and then I found it to be negative, it was going to tell me something about myself. In fact, I would say this is wrong. Why? Because a positive tells me that this is a spontaneous cell. So it tells me that this is a spontaneous cell. Okay, so I am having a spontaneous cell or a spontaneous reaction taking place here. A reaction that does not need external energy to drive it. Okay, this reaction will not be driven by external source of energy. It happens all on its own. But remember, back to the beginning of the lesson, we are taking advantage of the fact that P tends to give electrons to Q. That's what we're on its own, naturally. No one pushing, no one doing anything. Together, they just decide to what? To exchange these electrons spontaneously, automatically. So this answer being positive is actually a show that the reaction is spontaneous. Always remember that when you calculate a standard reduction potential, EMF or EMF of a galvanic cell, the answer that you get must always be a positive one. Once you get a negative one, it will mean that you are dealing with a non-spontaneous cell, and the galvanic cell can never be a non-spontaneous cell because a galvanic cell does not have external energy. Nothing is used to drive a galvanic cell. It actually drives itself through the conversion of chemical energy to electrical energy. I want to quickly do the second one to actually emphasize on my point where we were comparing tin versus cadmium. Okay, so we'll say E naught cell is equals to E naught cathode minus E naught anode. Okay, and then we go and look for these two. Here we are, we found the cadmium first, and then here we are, we have found the tin. There they are. Who's undergoing a reduction, which is the cathode? The one at the bottom. It has a higher oxidizing ability. Those are reasoning. So you will have minus 0.14 minus, okay, and then minus cadmium is minus 0.40. Okay, so if you put that into a calculator, you have minus 0.14, and then minus 0.40. There you go. Your answer you are getting there is a positive 0.26 volts. I hope if you are working with me, you are getting that answer. Again, the answer that we are getting is positive. It's positive spontaneous reaction. The spontaneous reaction does not require external energy to drive the reaction. Very, very important points there, grade 12, for us to take note of. Okay, so we've looked at writing the solid notation, we've looked at calculating the EMF, we've actually even looked at writing the net reaction, writing the half reactions. We have covered a lot of bases here, grade 12. So what I want us to do is just quickly run through an example question where we are going to look at how they actually ask these questions and how are we expected to actually answer them. Okay, so here's question 6, which says the cell in the diagram alongside consists of a cobalt CO electrode and connected to a silver Ag electrode. Is set up under standard conditions. It is set up under standard conditions. So in your head, you should quickly just remember those standard conditions. What are those standard conditions that they are talking about, right? So here is your electrode, and then they are saying define the term anode. 6.2, write down the oxidation half reaction for the cell. 6.3, write down a balanced net cell reaction. 6.4, write down the cell notation for this galvanic cell. And then 6.5, calculate the initial EMF of the cell under standard conditions. So this is 14 marks. 14 marks that I believe if you have been listening here, you should take all of these marks here. Okay, so what are we going to do? What we need is just our table. Okay, obviously to answer 6.1, define the term anode. That is the electrode where oxidation takes place. The electrode where oxidation takes place is the anode. That is just a simple definition, 2 marks there. We take them and then we run with them. Now what they want here is for us to write down the oxidation half reaction. For us to be able to write down the oxidation half reaction, we need to go to our cell. And then we say, what are we comparing in our cell? There is cobalt and there is also silver. I need to go to my table 4B because this is a galvanic cell. How do I know it's a galvanic cell? It has 2 beakers, it has the salt bridge, there's the voltmeter. Those are all things that are telling me that this is a galvanic cell. So what I need is go to my table and identify between cobalt and silver, which one is going to lose electrons, which one will undergo oxidation, which one will undergo reduction. Write those reactions, then I should be able to answer my question. Okay, so I am going to go and look for the cobalt, a CO2 plus based on the what? On the electrolyte, and also an Ag plus based on the electrolyte there. So I will go there, go to my table 4B, I will look for cobalt. Here's cobalt, I found it. there is cobalt there. Okay, there is my cobalt there. And then I'm also going to look for the silver Ag plus. There is the silver Ag plus. There is the silver Ag plus. Okay, it's underneath what I have actually drawn there. So from there, quickly, I draw the Z. I put in the arrows. What are the arrows for? They will tell me how to actually choose my my arrows when I am writing this reaction. So it's time to write, and I can quickly write the oxidation half reaction here just for myself. Then I would say the reaction looks like this: CO2 plus 2E, and then double arrows tends to CO. But I cannot write a reaction with double arrows. So what do? I choose this arrow. So it's going to be CO2 plus 2E, then choose this arrow, and then it is CO. For most of you, you leave it here. And if that is the case, totally fine with that, as long as you know how to proceed moving forward. But for the some of us, we like to actually flip it so that it tells a nice story, where we say we had a CO that turned into a CO2 plus because it lost 2 electrons. Nice story there that we have made up for ourselves there. So this would be the oxidation half reaction that is happening. If maybe we even ask for the reduction half reaction, then we would say, okay, there is the reduction half reaction, that is Ag plus, that actually gained an electron to become Ag. Okay, right. I hope you noticed something here. The CO actually lost 2 electrons, but Ag gains 1 electron. Okay, so this means for us to write the net ionic reaction, even though I'm going to just project the solutions here, we must balance here. I quickly want to explain this. Okay, I quickly want to explain this for you, grade 12, before I actually project the solution and go over them with you. It is important that we must balance. That then means for every 2 electrons that were lost by cobalt, we will need 2 ions of silver to take those electrons. I hope you understand. So cobalt will give 2 electrons, but when the electrons get there, 2 ions of silver will go for 1 pair of electrons, because cobalt will give the electrons in pairs. I hope you get me. So if we had our pickers looking like this, okay? So we are having our pickers looking like this, and this is cobalt, and this is silver. So this one will give the electrons going in pairs, all right? But when we get here, 1 silver ion only needs 1 electron. So it means for them to use both of these electrons, they will need what? 2 silver ions. Therefore, this must be balanced here. So for every 2 silver ions, then we'll be able to what? To use the 2 electrons. Then we end up having 2 silver atoms at the end of the day. So this is how we should actually balance it. If the electrons are not balanced, we should make sure that we balance them. And this is the idea behind the balancing. Then we can go there and do the cancellation, and then we say top plus bottom, arrow, top plus bottom. Okay, then you have your net ionic reaction there. So actually, let me just project the answers here, and then let's go over them together then, as you can see, right? So here's our reaction as we have actually written it down. CO gives you CO2 plus 2E. You see, it is actually written like I said. We are going to write it like how I like it written. So they even a marking criteria or guideline here to say if you write it like this, we give you 2 marks. Okay, but if you write it like this and you choose this arrow, it means you have chosen an incorrect arrow. Then this becomes wrong. Okay, if you write it like this with the double arrows here, then there are no marks at all. Okay, even this one, you are not given marks. Okay, forget this one here. This was a mistake. You don't get marks if you put double arrows. Okay, this one here is a mistake. Okay, I don't know what happened here, but this one is a mistake with the marking guideline. If you put double arrows, I'm telling you now, trust me, you are not going to get marks. It's a 0 out of 2. So please do not put double arrows. You write it like this. What they didn't put here, what they were supposed to put here is that if you leave it like this, you do get the 2 marks if it's written like this, because it's correct. Okay, the only thing that I've done is flip it around. But I always advise people to flip it around. It helps with the net ionic reaction. Okay, and then let's continue. Here is our net ionic reaction: 2Ag plus CO, 2Ag plus CO2 plus. This is what we have. It's that in this time we're starting with CO2 plus. That does not matter. It actually does not matter. And then the issue of the cell notation there. What will be the cell notation? Say double lines. The cell notation will look like this: double lines, line, line. Okay, and then what is happening in the cell notation? We had a cobalt turning in a cobalt 2 plus at 1 mole per decicubic meter, and then we had an Ag plus gaining those electrons to become a what? An Ag. In the cell notation, we don't need to do the balancing. Okay, in the cell notation, we don't need to do the balancing. So I wanted to give the one where there's balancing, so that I can show people what happens then. So in this one, we don't need to do the balancing, as you can see here, and you get your full marks when you write your cell notation like that. So you have taken the whole 14 marks, and it becomes free marks for you, grade 12. So that was me just trying to, let's go through a previous question paper where we are answering these questions and seeing if we can actually answer them correctly. Okay, so there was another one where we are calculating. That will be E naught cell cathode minus E naught anode. Okay, please no abbreviation there. So for the cobalt 0.80 minus for the silver, it is a negative 0.28 there. If you put that into your calculator, it should give you 1.08 there, and the answer is positive, because the answer must be positive when you are calculating for the E naught cell or the EMF of a galvanic cell. It tells you that the reaction is a spontaneous reaction, one that does not require. There is also another option that maybe people have been taught in class of calculating, where you actually do the half reaction, and then you do another half reaction, and then you do the net reaction, and then your half reaction there will be for the reduction. You do the oxidation then, and then you put it with its values obviously at the end, and then you do the subtraction there. You will get your answer like that. And then if you've been taught to do it like this, it's fine. You may continue doing like that. You're still in a correct path. However, I like this one because just in case, let's say just in case you are struggling here, I know for a fact that you are going to get a mark for the writing of a formula. I'm not saying write a formula without attempting. You must attempt. But I know for a fact that you will get that mark there. So it gives me that comfort to say there's a mark for the formula there. Okay, right. So grade 12, this would be your homework for the day. Try to go through this and see if you can work out the spontaneous electrochemical cell that is set up, right? And answer those questions. Can you get all of them correct, right? Because that's what I want with the galvanic cell total. Can you do this one here, which is also another question 6 there, right? And can you get all of them correct as well? This will be your homework. Quickly recap of what we have looked at today, grade 12. 1, we have defined a galvanic cell. We defined an electrolyte, and then we predicted the half cells in which oxidation and reduction takes place using the table 4b. Okay, table 4b, don't forget. And then we've written down the half reactions that occurs at the electrode oxidation, okay, also at the electrode reduction. We've done that, and we've shown how we should actually write it. We have written the overall cell reaction, or the net ionic reaction, also called the net ionic reaction. We have also done that as well. And then we have used the cell notation or a cell diagram to represent a galvanic cell, where we had those double lines, and then they were representing a galvanic cell there. We have also used the table of standard reduction potential, to calculate for the EMF of a standard galvanic cell using the formula E naught cell is equals to E naught cathode minus anode, anode. Okay, and then that's what we have actually looked at, and that is the galvanic cell for you. Okay, more practice will help you to understand this galvanic cell and to actually turn it into a DECA by the grade 12. All right, let's preview for our next lesson. Our next lesson will take place on the 8th of August from the same time. It will be Friday, 1440 up until 1600 hours. Topic again, the electrochemical cells still. So we are moving with electrochemical cells. We'll be looking at another cell, a different type called the electrolytic cell, and also we try to look at some of alternate energies that relate to electrochemical cells. There, we try to squeeze them in there so that people are aware of them. Grade 12, let us call it a day. Thank you.